In this video, I'm going to review this practice test and study guide. I'm going to go a little bit faster than usual because I'm a little bit pressed for time. Okay, the first one says write this in expanded form. So when we look at this, we see that we have multiplication going on. Everything's in the numerator. Therefore, we're going to put plus signs in front of each of these factors. So let's do that. We are going to have log to the base 10 of 10 plus log to the base 10 of x to the fifth plus the log of y to the 0 plus log z to the negative 2 power. Okay, whenever the base of the log matches the base of the exponent, there's a hidden 1 here. These cancel, that becomes 1. This, we're going to bring this 5 out front, and that's going to become 5 log to the x. Here, y to the 0 is 1, so we have log of 1. That's a base 10. If we were to put x here and do the whirlybird, 10 to the x would equal 1. Therefore, x would have to equal 0. So this entire term translates to 0. So I'm going to go ahead and erase any evidence thereof. And then finally, we have this minus 2 that can be brought out. So our final answer is going to be 5 log x minus 2 log z. Next one. Okay, whenever you see radical signs, just go right ahead and replace it with a fractional exponent. So I'm going to go ahead and do that right away. Don't forget your base. Next thing I'm going to do is apply the power rule. So each of these are going to get subjected to the 1/9 exponent. Okay, immediately I'm suspicious that I'm going to be able to do something with that in terms of evaluating it. Now what we're going to do is we're going to expand that by remembering anything in the numerator is going to have a positive sign. Anything in the denominator will be negative. As I'm doing this, I'm bringing each exponent out in front of the log. All of these are base 8, by the way. Notice minus signs in front of these arguments because they were in the denominator to begin with. Okay, now let's look at simplifying this. Like I said, I think this can be simplified. So we're going to have, if we had left that 1/9 up top, we would have had this. That would have been 3 to the 3rd raised to the 1/9 Then if we executed the power rule, we would have log to the base 8 of 3 to the 3/9, and that would be log base 8 of 3 to the 1/3, and then we would have brought the 1/3 out. So the final answer here should have been still minus next one. Okay, here we just recognize that we just have a bunch of factors here. They're all in the numerator. Therefore, everything's going to have a positive sign in front of the log as we pull them out. Next, we're going to pull the exponents out in front, and we're going to evaluate that. If I have log to the base 2 of 16 equals x, we do whirlybird. That means 2 to the x equals 16, and x is going to equal 4. So I'm going to replace that term with 4. Okay, now we continue writing, and we have 4 plus 3 log base 2 of x plus 2 log base 2 3x minus 7. What's your final answer? Okay, here they ask you to condense. So we're going to try to condense all these into one equation with one logarithm. Now, a couple things. The bases have to be the same, and they are. And also the coefficients in front of the log has to be 1. So we're going to have to move all of these coefficients up into an exponent position, and we're going to have to navigate the fact that this is z squared raised to a 6th power. Other issue, anywhere where there's a plus sign, the argument will go in the numerator. Anywhere where there's a minus sign, the argument will go in the denominator. So let's do that. We're going to write log once. It's the same base. We know there's a fraction. Okay, what goes in the numerator? We have x. We have y to the 5th. Now when we get to z, we are going to put that in the denominator, and we're going to multiply the 6 by the 12 via executing the power rule. I'm sorry, yes, that should be a z. And then we're going to have z to the 8th. The other thing we notice is that these z's can be combined. Whenever you multiply with a common base, you add the exponents. So our final answer is going to be log to the base 9, xy to the 5th, z to the 20th. Okay, they want us to condense this. So what's going on here? This 2 has to come up top. They're both the same base, so we can condense them. This has a negative sign. So this argument's going to go in the denominator. That has a plus sign. That's going to go in the numerator. So let's do that one. We write the word log only once. The base is understood to be 10. X plus 3 in the numerator. X minus 2 squared in the denominator. That's the basis of bringing that 2 up there. That's where that comes from. Again, the fact that that's negative puts this whole construct in the denominator. Next one. Okay, they want us to solve for x. I probably could make this bigger. I apologize. Should have done that at the beginning. My apologies to the audience. Okay, where am I? I'm here. Okay, so we're working on A over here. Our goal is to solve for x. Okay, couple things. The intuition tells me that the action's at different levels. So at some point in this problem, we're probably going to have to flip this and take the opposite of this exponent. The other thing I notice, we have 8s, we have 16s. That means more than likely 2 is going to be the star of this show. So let's go ahead and flip right from the beginning. On the left, we're just going to rewrite 8 to the minus 2x minus 7. On the right, we're going to flip that to 16 over 1, and we are going to change the sign of that exponent to its opposite. Okay. Next thing I'm going to do is I'm going to replace this with 2 to the 4th and this with 2 to the 3rd. As usual, 2 is the star of the show in a problem like this. Sorry. Now I'm going to distribute the power rule on both sides. The fact that these have common bases and this is an equal sign means we place these equal to one another. These exponents have to equal one another because we have a common base and we have an equal sign. Negative 6x minus 21 is going to equal negative 12x minus 4. And when you solve for x, you will get x equals 17 over 6. Okay, next one is over here. Very similar problem in that the action is in the denominator. Here the action is in the numerator. My plan is to flip this, change that sign, then get a common base between these two. That's 4 squared, that's 4 to the 3rd power. So that is our intuition on this problem. So let's go ahead and immediately flip the 1 over 64 to 64 over 1. And then change that to a negative x minus 2. We're going to set that equal to 16 to the x. Now we're going to replace 64 with 4 to the 3rd. Negative x plus 2 equals 4 squared to the x. We're going to distribute, and then we're going to set these equal to each other. We're going to get 4 to the negative 3x plus 6 equals 4 to the 2x. We now can set these exponents equal to each other. We get 2x equals minus 3x plus 6. 5x equals 6, and so on, and you get x equals 6 over 5. Next one. Sorry. Okay, here we're still asked to solve for x. So let's look at this one. First thing that comes to mind when I see this is that I'm going to end up doing whirlybird. So let's do that right off the bat. We're going to have 3 to the 4th is going to equal that argument, 2x minus 9. 3 to the 4th is going to be 3 squared times 3 squared, which is 9 times 9. That's going to be 81. And when you solve for x, you get x equals 45. Okay, over here, first thing I'm going to do is I'm going to divide by 5. And then I'm going to look for common bases. That's my game plan. So when I divide both sides by 5, I get 4 to the x plus 3 equals 2. The most obvious common base is going to be 2. 2 squared, x plus 3 equals 2. I'm going to distribute that. We're going to have 2 to the 2x plus 6 equals 2 to the hidden 1. I'm going to set that equal to that. 2x plus 6 equals 1. Always look for a common base. If you can't find a common base, that's when logarithms come into play. Okay, still looking to solve for x here. We have whirlybird. There's a hidden 10 here. There's a hidden 10 as a base. We're going to go 10 to the 3rd equals that. 10 to the 3rd equals 1,000. Equals 4x plus 1. 4x equals 999. And x equals this bizarre answer, 999 over 4. So again, just recognizing that there is a hidden 10 here, whirlybird equal to the argument. Pretty straightforward. Next. Okay, what's going on here? This is an interesting problem. We have whirlybird. Let's start with that. Okay, so we're going to have x to the 4 equals 1 over 81. 81 is 9 times 9, which is 3 squared times 3 squared, which is 3 to the 4th. So now we have x to the 4th equals 1 over 3 to the 4th. How are we going to handle that? Let me show you a beautiful trick. Remember, folks, our goal here is to solve for x. X is being raised by the 4th to the 4th power. How do we get x to the 1st power? That's our goal. If we get x to the 1st power equals something with no exponent other than 1, nothing out front here, no negative, we have solved for x. So how do you get x to the 4th to equal x to the 1st? What can we raise x to the 4th to get x to the 1st power? Well, none other than its reciprocal, 1 over 4. So what we're going to do here, folks, is we're going to raise both sides of this green equation to 1 over the 1/4 power. This is a nifty trick. This now becomes x to the 1st as promised. Over here we're going to have 1 to the 1 over 4th power, which I'm immediately going to erase that because it's just 1. And on the bottom we're going to have 3 to the 4th times 1/4. Be very careful of your fraction there. And that's going to give us 1 over 3 to the 1st, or 1 over 3. That's your final answer. So again, when you're solving for x and the x has an exponent, you get it to 1 by multiplying by the reciprocal. You of course have to do the opposite side. When you're faced with multiplying 3 to the 4th times 1/4, don't be cavalier. Set this up so you can clearly see that these 4's cancel out. Otherwise, you'll do something inadvertent, like call this, 3 to the 1/16 or something. So get these lined up, cross those 4's out, and you end up with 3 to the 1st power. Okay. This one, I'm not sure if this was a misprint or something, but we're going to move to this one over here. Okay. Okay, what's going on here? Over here, on the left side of the equation, we have log to the base 3, log to the base 3. That means we can condense these. Over here, this looks like something I might be able to evaluate, as in 2 to the something will give me 32. So let's explore that. On the left side, we're going to condense this by writing log just once to the base 3. We're going to put 6x plus 5 in the numerator. Why? Because this has a positive sign out front. Here, this is going to go in the denominator. So we're going to have 2 in the denominator. Now we're going to set that equal to the opposite side of the equation, which I believe we can evaluate. So let's look separately at log the base 2 of 32, set it equal to x. We do whirlybird. 2 to the x equals 32. We know that 32 is 8 times 4. We know that 8 is 2 cubed. We know that 4 is 2 squared. So lo and behold, 32 ends up being 2 to the 5th power. Recall, when we have common bases, we add the exponents. So this is going to be 5. X is going to be 5 here. Okay, so let's erase this. Okay, so now what are we going to do here now? So now we have this situation where we have this argument and this base. We're going to do whirlybird. So we're going to set 3 to the 5th equal to that argument. Turns out that 3 to the 5th power is, let's see, I'm missing a 2 here. Okay, what did I do here? 3 to the 5th equals 6. Okay. No, I'm okay. I gotta multiply both sides by 2. I apologize. There we go. So 3 to the 5th power is going to be 3 squared times 3 squared times 3 to the 1st, 9 times 9 times 3, 81 times 3. I do these this way. 3 times 8 is 240 plus 3. So this 3 to the 5th is going to be 243 times 2 is going to be 486. So we're going to end up with 6x plus 5 equals 486. And when you solve for that, you get a funky number, 481 over 6. So what we learned from that: condense, evaluate. Look for things that you can evaluate. Okay, what's going on here? Okay, similar problem in that these bases are the same. That's going to allow us to combine these arguments. This I'm not sure I can evaluate. We got 5s, we got 36, which means 9s and 4s and 6s and 5. I don't think we're going to be able to evaluate that. But let's take a look at this. Okay, no, the other thing in my intuition is, if I get something that I can't evaluate on this side of the equation, here's the other thought that pops in my head. I'm going to be able to condense this left side to log to the base 5, and then I'm going to have log to the base 5 with an argument, equals log to the base 5 of an argument. And I'm going to end up being able to set the arguments up equal to one another. Okay, so let's condense these. They both have positive signs in front. Therefore, they both are going to end up in the numerator. And the opposite side is going to stay the same. And we have just what I was alluding to. We have log to the base 5 of that equals log to the base 5 of that. That means we could set them equal to each other. I'm going to go ahead and distribute this x as I write this down, i.e. x squared and minus 9x. We're going to bring the x squared on the same side of the equal sign. We recognize this as x minus 12, x plus 3 equals 0, x equals 12, or x equals minus 3. Okay, now it's very important. This is a very important point. When you get your possible solutions, you have to go back in the original equation to check them. You don't go over here at the condensed equation. You take each of these, you, in your mind, put them in for x and see if you still have a legal equation. Specifically, do the arguments stay positive? We put a 12 here. That's fine. However, if we put negative 3 here, we get the log of a negative argument. No good. That's your final answer. 12 and 12 alone is your final answer. Okay, now what's going on here with this monstrosity? Okay, this one I'm going to have to rewrite, unfortunately, to show you how to do this. Something like this, you always go back and check that you transcribe correctly. Otherwise, it's the quickest way to make a silly mistake. Okay, so I go back and I check my work. Log base 4, x plus 2, log base 3. Okay, so this is how you handle these things. You set this equal to a letter, okay? So I'm going to choose D as in Dartmouth. So this becomes log to the base 2 of capital D equals 0. Okay, so if this all equals D, okay, all of this equals D, then you have the log to the base 2 of D equals 0. So now you do Whirlybird. So 2 to the 0 equals D. 2 to the 0 is 1. So 1 equals D. So now what I do is I take D and I set that equal to 1. Sorry for all these prestidigitations here. Okay, so that's D, and that's equal to 1. So now what do we have? We have some argument in here, and if we do Whirlybird, we find that that argument, which is log to the base 4 of x plus 2, equals 3 to the first power, which equals 3. Now what do? We do Whirlybird. And we have 4 to the third power equals x plus 2. 4 to the third power equals 64. And x is going to end up equals 62. Okay, so that's the type of problem you might want to rewind and look at that again. But the crux of it is, we have log to the base 2 of this mess equals 0. 2 to the 0 equals 1, which equals this mess. So then we just keep doing that over and over until we are finished. Okay, here they ask us to solve for x, so let's do that. Here we're just going to be using big time calculators. Okay, the first thing I think of when I see this is I try to get a common base. And I think to myself, okay, who's going to be the star of this show? 2 maybe? It doesn't really work. If you raise 2 squared, you get 4. 2 to the third power is 8. 2 to the fourth is 16. It won't work. Then I ask myself, 5. It doesn't matter that 5 times 2 is 10 or 5 times 4 is 20. What matters is, can you raise 5 to something on both sides? You can't. So at the end of the day, you cannot get a common base here. And when you can't get a common base, you take logarithms. That's the only way to solve an exponential equation. Okay, so we're going to take the log of both sides, and we're going to use log of base 10 because there's a 10 here. So that's how I rationalize that. When you have, in other words, we could have used natural log. You want to use either log or ln because both of them are calculator friendly. But don't forget, there's a hidden 10 in here. And whenever you are taking a log with a base 10 and the exponential part of the argument has a base of 10. In other words, let me start again. Whenever the base of the log matches the base of this exponential expression, these cancel. So we're going to have negative 3x equals log of 20. You're going to divide both of these by negative 3 and plug that into a calculator, and you get negative 0.434. Okay, over here, there's no way you can get a common base, so you're going to take logarithms. Really no benefit to taking natural log versus regular log, but we're going to go ahead and do regular log. So we're going to have log of 7 raised to the x plus 2 equals log of 60.3. This exponent comes out front. So you have x plus 2 times the log to the base, log of 7 equals log of 60.3, sorry. Divide both sides by log of 7. You get whatever that number is. X plus 2 is going to equal whatever the log of 60.3 divided by log of 7 is, and then subtract 2, and that's your final answer. Sorry to rush, but like I said, I'm a little pressed for time. I apologize. Okay, what's going on here now? Okay, more of the same, where we have to solve for x. Okay, so I'm looking at this problem. I have the log of a relative mess in here, but don't forget you have a base 10. So what I'm going to do is I'm going to do whirlybird, and I'm going to say 10 to the negative first power equals that. So 10 to the negative first power equals log base 2 of 5x. Don't get intimidated here. You know how to handle that. That is 10 over 1 raised to the negative first. It's the same thing as 1 over 10 to the first. So all we did was make this a fraction to make it more clear, flip it, and change the sign. So now we have I'm going to change 1 over 10 to something calculator friendly, and I'm going to do whirlybird. So 2 to the 0.1 power equals 5x. And when you do that in a calculator, you get x and divide by 5, you get 0.214. Okay, next one. Over here. Now here, first thing we're going to do is clean up all this mess and see if we get a common base. So I'm going to subtract 10 first and divide by 4, and I'm going to end up with e to the x plus 2 equals 5 over 2 once I reduce 10 over 4. can't get a common base here. So here we need to take logarithms, but because of that e, you're going to want to take the natural log of both sides. Because when you have the natural log, by definition that's a base e. Whenever the base of the logarithm matches the base here in the argument, these cancel. And you are left with just the exponent. X plus 2 equals ln of 5 over 2. You subtract 2 on both sides, and that's what x equals. Next one. So again, the learning point there is whenever you have e, you use the natural log so that you can use that trick where the ln of e to a power cancels out, just like log to the base 10. These cancel out, and in each case you're left with the exponent. Okay, what's going on here? So in this problem, we are simply going to move things around to try to get ln by itself and go from there. So first thing I'm going to do is I'm going to subtract 10 from both sides, and I'm going to get 15 over here, and then divide by 3. That's going to give me 5. So I'm going to have, when all the smoke clears, ln of 6x plus 5 equals 5. There's a hidden base e. I'm going to do whirlybird. E to the 5th, which is very calculator friendly. You plug in e to the x and you hit 5, and that gives you a number. And when you do all of that, you end up with e to the 5th minus 5 over 6. And you can do that in a calculator. Okay, let's look at this guy here, see what's going on. All right. What I say to myself is, we're going to combine these into one log. You have the same base on the opposite side. We're going to bring that up probably. And we're going to end up having the natural log of something on the left equals the natural log of something on the right. And we're going to set the arguments equal to each other. That's my intuition here. Okay, so the first thing I'm going to do is I'm going to combine these. They are both in the numerator because both of these are positive, and the ln is only going to be written once. So we're going to have this, and we're going to bring this 2 up top, excuse me. So just as we predicted, we have natural log of this argument equals natural log of that argument. That means the 2 arguments are equal. So as I'm writing down at the next level, I'm going to FOIL this. So that's going to give me 2x squared minus 4x minus 3x plus 6 equals x squared. I'm going to simplify, bring this on the other side, and I'm going to end up with x squared minus 7x plus 6 equals 0. Okay, so even as I'm writing this, I'm saying to myself, okay, I'm going to try to factor this, and whatever I get, I need to check the original equation, not the condensed. Okay, so this is going to be x equals positive 6 or x equals positive 1. Remember, either of these can be 0 to make this entire side of the equation 0. So we set that equal to 0, x minus 6 equals 0, x equals plus 6, x equals plus 1. So now we take this and we plug each of them in the original equation to make sure that we don't violate any principles by creating a negative. We don't do it down here or in here. We do it in the original equation. And we find when we put x equals positive 1 there, that becomes negative. So this gets rejected, 6 gets retained. That's our final. What's next? Okay. So G is a very interesting problem. We've seen these before. I've talked about them on some of my other videos. This is a hidden quadratic equation. In the previous problem that we just did, we had this. So what do you notice? There's a hidden one here. This exponent is twice that. Whenever you have this exponent 2 times that, you have a hidden quadratic equation. Look what's going on here. 4x is twice 2x. Okay? This is a hidden quadratic. Specifically, this is e to the 2x squared plus 5 e to the 2x minus 24 equals 0. And when you see this and you recognize that this is a hidden quadratic because this is twice that, you take that, put it in the parentheses, and square it. Okay, because again, if you did the power rule, 4x, 2x times 2 gives you 4x. Okay, so the way I like to do these is, it's just easier for me to set e to the 2x equal to the letter u, and that gives me u squared plus 5u minus 24 equals 0. And then I factor this as u plus 8, u minus 3 equals 0. Therefore, u equals negative 8, or u equals positive 3. Now I bring the e to the 2x back into the loop, and I have e to the 2x equals negative 8, or e to the 2x equals 3. So all I did was put this e to the 2x back in here for u. Now when we look at this, the only way to solve this is to take the natural log of both sides. So if we take the natural log of this expression on the left, we would have natural log of e to the 2x equals natural log of negative 8. We immediately reject this because you cannot take the natural log of a negative. Over here, we would take natural log of e to the 2x equals natural log of 3. That has a base e. We would get 2x equals 3, and x equals, 2x equals natural log of 3. And the final answer for x is going to be ln of 3 divided by 2 is going to equal x. Okay. Very interesting problem. Okay, over here, h. We're looking for common bases. No such luck. You can't get a common base between the 3 and the 5. So what we're going to do here is we're going to have to take the natural log of both sides. So when we do that, we have the natural log, or we could do regular log. Let's do that just in case something cancels out. Let's see what we get here. Log to the base 10 okay, so what I would do is pull this out front and pull that out front. Okay, Then I would divide both sides by log of 3. And I would get a number here. Sorry. I would get this. Then I would divide both sides by x plus 4. And I would get 2x minus 1 over x plus 4 equals whatever this comes out to. And then I would cross multiply and solve for x. That's how I would proceed there. Okay. Now it looks like we talk about applications. All right. So now we're moving into a different part of this review. So let's back off a little bit here. Okay. So for this one, if you read through this problem, they say the number of decibels is 10 times the common logarithm of the number of decibels is 10 times the common log, that's log, of the relative acoustic power. And then they just give you relative acoustic power, so you just have to take 10 times the log of each of these numbers. So I'll do the first one or two, and then that's about it. So 10 times the common log, which is log to the base 10, of the relative acoustic power. So the first one is going to be this. 10 times the common log of the relative acoustic power. So what does that equal? Well, let's try to evaluate that. If we have log base 10 of 1 equals x, we have 10 to the x power equals 1, x has to be 0. So this whole thing is going to evaluate to 10 times 0, which equals 0. Next one, 4,000. So all we do, folks, is just replace the 1 with 4,000. This we can't evaluate because 10 to the x doesn't equal 4,000. So here you put this in your calculator, multiply it by 10, and you get, what did I get for this? 36.02. And you do the same thing for this one and you get 88. So I'm not going to bore all of us by adding in that math. Let's go down to this one. Okay, this is a compounding interest problem. So let's take a look at this one. You have $14,000 to invest, so the principal amount is going to be $14,000. And then they ask you, which investment yields a greater return over 10 years? So T is going to equal 10. 7% compounded monthly. Or 6.85% compounded continuously. Okay, so you may have seen my previous video where we talk about these in great detail, but the bottom line is when you're compounding monthly, you use this formula. When you're when you're compounding anything but continuously, you use this one. And if you did watch my video, I use the mnemonic that we have Nosy Nancy here. She has to appear twice, and the R is the rate in decimal form, and N is the number of times compounded per year. So if we're doing this monthly, here N is going to be 12. So let's do the math. We have 14,000 times 1 plus 0.07 over 12 times 12 times 10. And when you plug all of that in a calculator, raise it to the power of 120, you end up with 28,135 for part A. Part B, whenever you see the phrase compounding continuously, we use a different formula. And that formula involves E, and Nosy Nancy gets pushed out of this equation. She is not involved because you are not dividing, or excuse me, you're not compounding a certain amount of times per year. You're compounding continuously, and that's where the exponent E comes in. So this becomes 14,000 times E. The rate again has to be in decimal form, 0.0685, that's this, times 10, and when you do the math, you get a number that's 27,772, and this is greater. So your choice would be to compound monthly rather than continuously. Okay, this is the last problem. It's a half-life problem. Whenever you have a growth or decay problem, you are going to use this formula. A of t equals a sub 0 e to the kt. All these problems are the same. They're going to give you enough information to allow you to find k. That's going to give you the model of the equation. Once you have the model of the equation, you can answer anything they throw at you. In this case, they want to know the time it will take to decay to 80%. But let's do part one. Let's find the model. Now, again, as I allude to in my other video, when they tell you that the half-life equals 12 hours, that is a huge amount of information. Here's why. They're telling you that when the original amount is 1/2, let me start again. When the amount of aspirin that you have is 1/2 the original amount, okay, that's 1/2 of a sub 0, the time is 12 hours. So by giving you the time when this reduces to half of itself, they've given you the model equation. All you have to do is solve for k. Why has it become so easy? Because these a sub 0's beautifully cancel out, and we change this 1/2 into something that's calculator friendly, which is 0.5. And we have e to the 12k. I like to reverse that. It's just easier for me. We're going to take the natural log of both sides. And we choose natural log because e is involved. And whenever e is involved, we can use this trick. So now we're going to have the ln of 0.5 equals 12k. And when you do that in your calculator, you get the fact that k is going to equal negative 0.058. And it makes sense because you're always going to get a negative k value when you have decay problems. Okay, so now we are in the catbird seat, and here's why. Because we could handle anything that they throw at us. First thing we're going to do is we're going to write the model equation using the k that we found. That model equation is as follows. Okay, now we are ready. So let's get rid of everything else but that model equation. Okay, we use that very powerful phrase that the half-life was 12 hours. We appreciate all that information that gave us. It allowed us to get this equation. Okay, what do they want to know? I can't even remember what they wanted to know because I know whatever it is, I can handle it. Okay, 80% of its original value. So how long will it take? In other words, what is t for you to have 80% of the original amount? So what's 80% of the original amount? None other than 80% of a sub 0. We don't know what t is, but we do know that these cancel out. So now we have 0.80 equals e to the negative 0.058t. How do we solve this? We take the natural log of both sides. Why do we use natural log instead of regular log? Because natural log has a base e. Whenever the base of the log matches the base of the argument, these cancel. So we have ln of 0.80, which is very calculator friendly, equals 0.058t. This is going to end up being a negative number, and you're going to get t equals 3.84 hours.